All right, welcome back to the Explainer. Today, we're diving into something called Rényi Entropy. Now, I know what you might be thinking, another entropy? But stick with me, because this isn't just one more way to measure information. Nope, it's an entire toolkit, and it lets us look at data in some really new and powerful ways. So let's jump right in. Okay, let's start with a simple question. Which one of these is more surprising? A coin landing on heads, or getting a report of snow in the Sahara Desert? I mean, a coin flip, that's a 50-50 shot. Not surprising at all, right? But snow in the Sahara, that is a huge deal. It's a super rare event, and because it's so unexpected, it's absolutely packed with information. And that's the key idea we need to grab onto. The more surprising something is, the more information it contains. But, okay, how do you actually measure something like surprise? You can't just eyeball it, you need some kind of mathematical ruler. And for decades, the one and only ruler, the gold standard, came from the legend himself, Claude Shannon. His big idea was Shannon entropy, and it basically became the way to put a single, hard number on the average uncertainty of, well, just about anything. So here's what we've got on tap for today. We're going to ask, is one ruler enough? Then we'll dig into Rényi's information toolkit. After that, we'll see where it's used, from the quantum world to AI. And we'll wrap up with why a more flexible future is so important. All right, Section 1, one ruler for information. Let's talk about the limits of having just a single measurement. So Shannon's genius was all about calculating the average amount of surprise you could expect from any given situation. You know, like comparing a totally fair coin flip to, say, a loaded die. Shannon's entropy gives you one single powerful number that captures that overall uncertainty. And honestly, it was an idea that completely revolutionized communication theory. But here's the catch. What if the average isn't what you care about? What if your job is to focus only on the most common things that happen? Or, and this is the big one, what if your entire mission is to hunt for the super rare, outlier events? You know, the snow in the Sahara moments. All of a sudden, that one-size-fits-all average ruler, well, it might not be the right tool for the job anymore. And that, right there, gets us to the heart of the whole thing. Shannon gives us that one perfect gold standard ruler. It's incredible. But Rényi gives us something completely different. It's a full-blown toolkit, a whole family of different measures that you can tune and adjust depending on exactly what you're looking for. Okay, let's dive into that toolkit. Section 2 is all about Rényi's information toolkit, building a more versatile ruler for information. So, picture this. It's 1961. A little over a decade has passed since Claude Shannon totally rocked the world with his paper on information theory. Then along comes this mathematician, Alfred Rényi. And he wasn't trying to tear down Shannon's work, not at all. He was standing on the shoulders of a giant. He just realized that for all the new problems popping up outside of coding theory, scientists were going to need a more adaptable set of tools. And this was his solution, Rényi Entropy. The really clever bit, the secret sauce, is this little parameter he introduced called order alpha. Seriously, this one little variable is what turns a single measurement into an entire spectrum of measurements. It's pretty cool. Let's break down how it actually works. So think of it like this. If Shannon gave us a fantastic, top-of-the-line, but fixed-sized wrench, Rényi came along and handed us an adjustable wrench. Or, you know what, an even better analogy is a Swiss Army knife. It's one device, but it's got all these different tools packed inside. And each one is perfect for a specific job. You just have to know which one to pull out. So how does this whole Swiss Army knife thing work in practice? Well, it all comes down to that alpha parameter. Think of it like a dial you can turn. If you turn the dial low, to a value less than 1, you're basically telling it to become super sensitive to the rare events, those long shots. Now, what happens if you set that dial exactly to 1? Boom! You get classic Shannon entropy. It's literally built right in. Okay, but what if you turn the dial high to a value greater than 1? Now you're doing the opposite. You're focusing only on the most common, most likely outcomes. The power is that you get to decide what to focus on. Okay, this is all fantastic in theory, right? But where does this toolkit actually get put to work? Well, it turns out it's a huge deal in some of the most cutting-edge fields out there today. Let's move on to Section 3, from quantum to AI. I mean, seriously, because it's so flexible, Rényi's framework has just exploded into all these different areas, some that he probably never even dreamed of.
This is not some niche little mathematical tool. It's actively being used to crack problems in quantum information theory, deep statistics, and yeah, right at the core of modern machine learning and AI. First up, let's talk about one of the wildest applications, quantum information theory. In the quantum realm, things get weird, and Rényi entropy is absolutely critical. It acts like a kind of parent concept that brings a bunch of other important quantum entropies, like von Neumann or min and max entropy, all under one roof. And what does that let scientists do? Incredible stuff. They can use it to rigorously check the security of quantum communication protocols. And it even helps them get a better grip on one of the strangest ideas in all of physics, quantum entanglement. Okay, let's bring it back from the quantum world and jump over to something a bit more familiar, statistics and machine learning. In data science, Rényi's Toolkit is an absolute powerhouse. There's this whole field called information theoretic learning, and in it, Rényi entropy is often used as what's called a cost function. A good way to think of that is like a guide for an AI. It's telling the system if it's getting warmer or colder as it tries to learn and solve a problem. And this ability to guide the learning process, it's what helps power the very algorithms that do things like filter your data or classify images or recognize patterns. All right, let's bring it all together. Section 4, a more flexible future. Why does having a generalized toolkit like this actually matter so much? It really all comes back to Alfred Rényi's core insight. He just fundamentally understood that different questions demand different tools. Shannon's work was an absolute game changer for his field, for coding theory. But science doesn't stand still, right? We started asking new, different kinds of questions that just needed a new, different kind of ruler. And this is the main takeaway, the most important thing to remember. Rényi entropy isn't better than Shannon entropy. It's more general. It gives scientists and engineers that whole spectrum of tools we talked about. It lets them pick the right tool for the right job. Whether that means focusing on rare events, common events, or just the plain old average, it's all about having options. And that brings us to one final thought to leave you with. Let's be honest. We're living in an age where information is maybe the most valuable resource on the entire planet. What Rényi's work shows us is just how powerful it is to build flexible, adaptable tools to make sense of it all. So the question becomes, as our world gets even more complicated and the data gets even bigger, what are the new tools that we're going to need to invent next?